Okay, hello everyone. So in this lecture now we start talking about the technical details of carbon. Okay, so this is the first lecture on introduction to carbon. Okay, so before we go into making our own carbon materials and finding the application, let's see what what is carbon in nature. Okay, so many of you probably already remember that we have where does carbon belong in the periodic table. You probably also remember that its chemical symbol is C, and its atomic number, which means the number of electrons in carbon, that is 6. Okay. Now the atomic weight of carbon, and I have written weight here, not mass, not written atomic mass, for a reason. That is 12.0107. Okay. Now before we go further, let me also tell you about carbon isotopes. Do you recall the definition of isotopes? Basically, isotopes are different forms of the same element where you have the same number of electrons, but the number of protons and neutrons varies. Okay, so I have shown it in this picture. Carbon 12, carbon 13, and carbon 14. These are the three very well known isotopes of carbon. Okay, now in the case of carbon 12, you have 6 protons, 6 neutrons. Now these protons, neutrons I have shown just as these spherical particles for easy representation. Okay, in the case of carbon 13, which is about 1.1% in nature, 6 plus 7 in the case of carbon 14, which is only 1 ppm, parts per million in nature, you have 6 protons and 8 neutrons. Okay, among these 3 primary isotopes, we have carbon 12 and carbon 13, which are stable isotopes. Stable means they don't naturally decay. And the third one, carbon 14, is the radioactive carbon isotope. So often you hear about radiocarbon dating. For that we are going to use carbon 14. So we'll discuss a little bit about the radiocarbon dating as well. Okay. Now I said that I use the term atomic weight and not mass. Okay. If you think in terms of general physics, what is the difference between mass and weight? The definition of weight is m into g. Okay, so which means that you're factoring in the gravitational constant. Okay, mass remains the same and weight varies. For example, if I go on the moon, then my mass will still remain the same, but my weight will change. Okay, because the value g will change. But in the case of atoms, are we really factoring in the g? Are we really weighing an atom on a balance? Or we are saying that, oh, an atom on the moon will be different compared to an atom on the earth? The answer is no. Then why are we using these two different terms, atomic mass and atomic weight? Okay, the answer is as follows. Atomic mass is simply the summation of the protons and neutrons for any particular atom. So if I take C13, 6 plus 7, 13 is the atomic mass. Okay, but atomic weight, you will never say atomic weight for carbon 13 or carbon 14 or carbon 12 for that matter. You will say atomic weight is for carbon. Okay, why do we say that? Because atomic weight basically takes care of all the isotopes. So it is the weighed average of the atomic masses of different carbon isotopes, and then we get one value which we call atomic weight. So briefly or quickly, you can also calculate this by yourself. Just take these three values here: 12 multiplied by the abundance of carbon 12, 13 multiplied by the abundance, and so on, and then we divide it by 100 to take the weighed average, and then we get a number 12.011. In this case, 12.0107 is what I had written, and the reason for this difference in the number is because all of these values are approximate. In fact, they might even sum up to more than 100. These are approximate values. And also we have omitted many isotopes here. So approximately, when you have these exact numbers and you calculate with the exact 4 or 5 digit up to that, then you will get the number 12.0107. So that is your atomic weight. And this terminology is used this way mostly because you see, atomic weight is something that varies, but atomic mass remains the same. Okay, so that is the case also in some elements. However, mass and weight might be the same. Why? Because these elements might not have different isotopes. So if they are naturally found only in one form, in that case their atomic mass and weight is the same. Okay. Now the atomic configuration of carbon, that is very easy. You probably know it is 1s2, 2s2, 2p2. This we are talking about the ground state carbon. Of course, when it hybridizes, then things change. Okay. Fine. So now we said that carbon 12 is the most abundant form of carbon, and then there is also an application of carbon 14. What about carbon 13? Does that also have an application? Okay, yes, there is something called nuclear magnetic resonance spectroscopy, or NMR spectroscopy. Definitely chemists who are attending this class, they know what is NMR spectroscopy. Okay, now what we detect in this NMR spectroscopy, I will not go into the technical details, but we can actually measure the relaxation times of those nuclei that have a nuclear magnetism. So magnetism, if you think in terms of electronic magnetism, you will think that when there are unpaired electrons, for example in iron, then you will have magnetism, and that is actually correct. But nuclear magnetism is when you have odd number of particles inside the nucleus. So it has nothing to do with the electrons. Okay, so now when you have C13, then you see there is an odd number, and that is why the value of spin quantum number that you get is -12. Okay, so this particular atom of carbon is NMR active. Okay, so this is very extensively used in NMR spectroscopy. Okay. The third one, as I already mentioned, is radioactive, C14, and radioactive materials also have a half-life. So the half-life of radioactive carbon is 5730 plus minus 40-50 years. Okay, because you see, when we are talking about the age of a fossil, something that is maybe 5,000 years old, then 50 years don't make so much difference. So you have plus minus 40-50 years. So that is your error. 5730 approximately is the half-life of carbon. Okay, the last two electrons of carbon are in the p orbital, as you already see that it is px and py, and the pz orbital remains empty in the case of ground state carbon. But as I already mentioned, that in nature it's rather rare to find ground state carbon, because it always would form another carbon atom or some other atom and try to form a bond and get into a more stable stage. Okay, so let's talk a little bit more about the radiocarbon. You know that radiocarbon dating is used for dating the very old objects, for example, a fossil. So now, since every fossil, every remains of an animal, let's say you find some spider sticking on top of a stone, something like this, would contain some carbon. The reason is that because these are organic materials. So after a long time, after several thousands of years, when you have all the non-carbon materials or non-carbon elements have left the material, but then some carbon is always, we can detect it. Okay. Now also, if you find some carbon, that means there is also some natural abundance of carbon 14 in it, and that is how you can do radiocarbon dating. Okay. But exactly how is it done? Okay. So when there is any living objects, whether it's humans, it's animals, or even plants, let's take an example of a tree. So a tree would take some carbon dioxide from the atmosphere, but as long as the tree lives, it will keep on using that carbon dioxide for making things whatever it needs, and then there will be some waste from the tree also that will go back into the atmosphere, and then new carbon dioxide it will keep taking. So basically it will reach a steady state with the atmosphere. So the concentration of carbon 14 or carbon in that tree would be then equal to the concentration of carbon 14 in the atmosphere. So now we can guess what was this concentration in the atmosphere at various time points, and then we match the concentration from that from the value that we found in the experiment, and that is how we measure, or that is how we kind of guess the age of that particular object. Okay. Now there is also a certain type of instrumentation for this, and the instruments that are used for radiocarbon detection or measurements, they are basically beta particle detectors, because carbon 14 nucleus that emits a beta particle. Beta particle is nothing but an electron, or also it can be a positron. So these particles, when they are emitted, they are also very high energy particles. So high energy particle means if I throw something with a very high energy, what will happen? It can travel a long distance. So this is how these beta particles also, because of their energy, they can travel long distances without getting deviating from their path or without getting damaged. So this means that if I want to detect them and I use a detector, they will also reach the detector with a very high efficiency. Basically, it is also easier to measure carbon-14 compared to other elements. So that is how we use the carbon-14 for radiocarbon dating. Okay. So as I mentioned, whatever is the process of balance or the concentration of the carbon-14, that is valid for also animals and also for human beings, anything that is living. Okay, so now we just quickly look at it mathematically. You remember this radioactive decay law? What are the different terms here? N is basically the number of unchanged atom. Unchanged means radioactively unchanged. So these are atoms. So the number of unchanged atoms at any given time t is n. Okay, and n0 was the number of atoms at some point time point t0. Okay, because it is a decay, you can see it's an exponential decay, and that is why we have the minus sign there. And lambda is the decay constant, which is characteristic of every particular element, every particular material. Okay. Now, one more thing, probably you remember that what is the half-life when you have half of the radioactive material left? Okay, which basically you will define it like this, that this is the time interval, which is when your N0 becomes N by 2. Okay, so if you now insert these values into this this whatever equation 1, then you will get a value of T half for everything. So the general formula for T half is 0.693 by lambda, and this I'm sure that you remember this formula. Okay, so now let's quickly calculate it for carbon 14. So if let's say I'm doing some experiment, and in that experiment I found out that the value of half-life is 5745. Okay, so I said it in the previous slide that the number is 5730 years for the half-life, but also plus minus 40-50 years. So let's say if you take a value 5745 years, then how do you calculate the lambda? So very simple, 0.693 divided by the T half. The only thing I've done here is because conversion from years to seconds. So because the unit of lambda is or the decay constant is per second. So this is how you can calculate the radioactive decay constant for any element. For example, for your own self, you can also do it for uranium-36, and you can do it for many other elements if you know the half-life. Okay. Now, there are many archaeological sites where, of course, this is a very helpful technique. For example, this is a picture of Dholavira in Gujarat. So this is one of the Indus Valley sites. There were many Indus Valley civilization sites. Now there is one also in Ropar, and there, of course, you know the Harappa, Mohenjo-daro. So they are all connected, and historians are actually now studying the connection between them and the scripts that are found there. So there is a lot of work going on, but now it becomes very critical to find out the age of these sites, because the entire history of the country is related to that. So this is when you use, maybe you find some tree, or maybe you find some ashes, or maybe you find some, even an object which may contain some organic matter or some carbon. So this is how you use the radiocarbon dating. Okay, so you can already write many advantages of this technique. First of all, it has a very long half-life. Let's say if you want to find out the life of or the age of something which is 10,000, 20,000 years old, in that case, you cannot use an element which has only 10 days of half-life, right? Because then it would have already decayed in 10 days to its half of its concentration, and then further half and further half, and today the concentration would be so low that you would not be able to find out. So carbon in that sense has an advantage over other elements. This is present in the biological objects, and also it's relatively easy to make reference standards. Reference standards means whenever I do some analysis, I need to have a reference, right? What is the value that I expect? So because carbon is available in everything, it's easier to make these reference standards using the labeled carbon, or labeled carbon means the radioactive carbon. So where you have replaced the carbon-12 atoms also with carbon-14 atoms, that is what you call a labeled compound, radio-labeled compound. And such compounds, in the case of chemistry, they are then also used for many other applications. For example, learning the mechanism of a certain reaction. So if I mix three things, A, B, and C, In the case of A and B, I have carbon 12, but in the case of C, I have carbon 13. Oh, sorry, carbon 14, and I can detect it. Also, we can do it with carbon 13, but let's say right now we talk about carbon 14, which can be traced because it's a radioactive isotope. Now, when I mix these three things, I want to see what is attaching to which one at what time, how this material is splitting, and what is the new things that is being formed. So I want to trace my carbon 14 atom, which I can do then. And this is how I can understand the mechanism of a certain reaction. So it's also in radio analysis and in chemistry, it is widely used, the radiocarbon material. Okay. Altogether, as I said, the cost of reference materials, also the cost of the instrumentation, everything is reasonable for the case of carbon. Of course, it can always be expensive compared to something, but altogether, this is a very common technique, and we all know about it, that for dating a lot of archaeological objects, this technique has been widely used. Okay, limitation, everything has certain limitations. So one big problem with carbon 14, so in general, cost and this and that, those are very common limitations. You can write it for everything. But one technical difficulty with carbon is that we are kind of dependent on our knowledge of the atmospheric carbon at any given, or the concentration of carbon 14 in the atmosphere at any given point. But that can change locally. For example, in the last 50 years or last 100 years, we all know that the concentration of carbon in general has increased a lot in the atmosphere, which also means that concentration of carbon 14 has increased a lot. Now, this may have happened also, let's say 20,000 years ago, there was a big fire, and that is why the atmospheric concentration of carbon increased. Or because of any other, even meteorite hitting and things like that. So, because of these reasons, the atmospheric carbon concentration may not be exactly what we think, but still it's a good approximation. Okay. Of course, the when we are doing radiocarbon dating, then it has to contain carbon. The fossil has to contain carbon, which is the case with most of the fossils. But sometimes what happens is you find only the bones. Bones of humans or bones of animals. And if you then want to detect, for example, the oldest human fossil available in the world is of a female who existed more than 3 million years ago. And there is a name given to that fossil, Lucy. So there are many bones of Lucy that have been found, and based on the dating of those bones, then the age of that type of human was detected. However, because we only had bones, and even the bones had gone through 3 million years, and that is why there was no organic matter found there. In that case, you need to use more sophisticated techniques. You can also do radio dating with other elements. So, but that may be very much more expensive. But that is so. Inorganic material cannot be detected. That is another limitation. Okay. And one more thing, lastly, is that if something is very old, more than 40,000 years old, then the technique becomes a little bit weak anyway, because we don't have very good information about the atmospheric carbon at that time, and also the concentration of carbon then becomes so low, because you see, in 5730 years, the concentration of carbon 14 becomes half, and then half of that, and then half of that, and then half of that. So at some point, it is the concentration. If something has been decaying for more than 40,000 years, then the concentration then becomes so low that you are not able to detect it. But altogether, this is a very handy technique. My goal to tell you all of this here was to, because I want to tell you that the radiocarbon dating is based on carbon 14 and not carbon 13, because sometimes people confuse that, because there is, you remember carbon 12, 14. Now there is also something called carbon 13. And that is not radioactive. That's a stable isotope. In fact, that is what we talk about now. Okay, so this the carbon 13 is the one that has an odd atomic mass, right? It is 13. And when there is the atomic mass is odd. So you will have a spin half or spin 3 by 2, minus half, minus 3 by 2, 5 by 2. So you will basically you will have one unpaired electron. You will find the spin quantum number of that nucleus. Okay. Now the fundamental principle of this NMR spectroscopy is that if you keep these kind of materials or these kind of elements in an external magnetic field, then in the presence of this external field, these spins can align, and then when the field is removed, they can relax. And based on these relaxation times and based on these alignment of spins and the number of spins in that align and which don't align, what kind of relaxation mechanism they have, based on this, different elements can be analyzed, and this is what we do in NMR spectroscopy. What I also would like to tell you is that MRI, if you remember the medical imaging technique, MRI is also magnetic resonance imaging. Why we call it MRI? This is also actually based on the exact same principle as NMR. This is based on the principle of, not exact same principle, but it is also based on the principle of nuclear magnetism. And we, however, also technically call this technique nuclear magnetic resonance imaging. So it is actually, the actual name of MRI is NMRI. But medically the term nuclear was removed because people get afraid whenever they think anything is nuclear. They think that now something bad will be done to my body. So that is why for the medical purposes it's called only MRI and not nuclear MRI. But this is based also on the same principle of nuclear magnetism. But here what we do is we take the protons, because there is a lot of water in our body, right? And hydrogen also, it has the odd number, it has only one proton. So actually proton is also then NMR active, and since our body contains a lot of protons because we contain a lot of water, that can be then imaged using MR technique, and then based on that you can find out what is wrong with the body. Now this whole thing I'm telling you because you will see that carbon, when we talk about the applications of carbon is used for a lot of biomedical applications. For example, making the bone implants, or also different kinds of even equipment that are used for biomedical imaging purposes and so on. Carbon is used for manufacturing those things, and in that context you will hear a lot that carbon is MRI safe, or carbon is X-ray safe. So why is that the case? So this is what I'm trying to describe a little bit here because it often gets confusing. Now carbon-13 is NMR active, but importantly in the case of MRI it is not important because we are only imaging proton. We are not really doing carbon-13 based imaging. And why we are not doing it? Because the natural abundance of carbon-13 is only 1.1%. In the case of hydrogen, well, all the protons are NMR active, so the concentration of signal is very high. But in the case of carbon-13, you will never get enough signal to do the imaging. Then why are we doing spectroscopy? Because in the case of spectroscopy, we can artificially make something which is labeled, this time labeled with carbon-13, not 14. So we can always make this kind of material for the purposes. Also, there are some coupling mechanisms between hydrogen and carbon that we want to understand for a lot of organic materials for the analysis. So carbon-13 NMR is done, but in the case of MRI, carbon-13 is not quite used. So don't get confused by that. Why then carbon is MRI safe or MRI silent? Well, two reasons. Because number one, it does not really interfere with the electromagnetic field that is used during MRI, and that is why there are no artifacts. The images are not distorted. And number two, which is actually a more important reason, that carbon's it is electrically conductive, but the conductivity is low enough. And as I also mentioned previously, that we can tune the conductivity just by by changing the preparation method. We can also have carbon with a little bit high conductivity, with a little bit low conductivity, so that the one that we use in biomedical applications, that has a relatively low conductivity, good mechanical strength, but low conductivity. And that is why this particular carbon does not have a lot of eddy currents produced in it. So you know that whenever there is a conductive material which is kept inside an active magnetic field, then eddy currents are being produced inside the material. Now in the case of metals, you have a lot of eddy currents, which also mean that the metal can heat up at some point. So if somebody has a metal implant, prosthetic arm for example, somebody has it made of metal and then you do MRI, then the implant itself can heat up. But on the other hand, when you use a carbon implant, then there is a much lower probability that it will heat up or something will happen to it, because the eddy currents, compared to metals, the conductivity of carbon in general is very low. So because of these reasons, you can use it for making implants, human implants. Okay. Yeah, so these are not just pure carbon materials, but carbon-based composites, CFRPs. That is what we will learn about them, and how we make the implants. We'll also learn about that. Typically, we can do 3D printing for making the exact shape of the bone that we want, and so on. Okay, carbon is also transparent to X-rays. X-rays will completely pass through the carbon. And you know it because when you are when there is some X-ray of your body being taken, then you only see the bones, right? You don't see the polymers, you don't see the skin, you don't, because these are organic compounds which are primarily made of carbon, and carbon is transparent to X-rays. It lets them through it, not completely, but at least 70 to 80% X-rays can go through carbon, which also means that now if you have a bone implant, then you can, that will not interfere with the X-ray. So for example, somebody has a bone implant, but then you know, you want to take the X-ray to see, let's say I actually had an implant here, and then if you want to see if the implant is actually working properly, or the bone has joined properly or not, you know, after how long, if and so on. So if you want to measure the progress and you want to do the X-ray, then the material should not, the implant material should not be opaque to X-rays, right? Otherwise it will hide some of the information. So in the case of carbon, that is not a problem, and that is why we also use carbon for this is another reason for carbon's biomedical applications, which also, by the way, includes biomedical equipment. So the plates which are used for X-rays, and even the tables, and a lot of things that are used also in the equipment itself. So a lot of these things are then made of carbon-based composites and carbon-based direct carbon materials or carbon-based composites. Okay,